Hey guys, Mr. Hanley here, if you can't tell. We're going to be continuing discussing the physics of sound. Please turn to page 406 is where we're going to be picking up. We kind of covered all the way through where we were, through 405. You have to remember a sound wave is a pressure wave. That's kind of how we define it. Any kind of wave is a carrying of energy without carrying the medium itself with it. The medium itself can move, but the energy flows through the medium. And remember, I likened it to conduction of heat, not convection of heat, but conduction of heat, where the heat energy is passed from particle to particle, or person to person to person, or object to object, and it's kind of like sound moves pretty much the same way, and it's from particle to particle to particle. And remember I said, therefore, you can't have sound in space. You know, in space, no one can hear you scream, which is true because we can't hear in space. You can't hear any sounds in space. So we're going to talk about page 406, how we perceive sound. We can talk about sound in multiple different ways. The main two ways you can describe a sound. Let's say you hear a sound. You say, oh my goodness, I just heard a sound. I would say, well, what did it sound like? You would probably, unless you did some sort of imitation of the sound, you would probably describe it in one of two ways, most likely, and those two ways are pitch and loudness, okay? Unless, obviously, it has a familiarity to it, but if you heard like a noise, a note, you could describe it on pitch or loudness. What pitch is how high or low a note is. For instance, a high pitch would be, ah, a low pitch would be, oh, you know, that is, Mrs. Hanley's eating dinner right now, right next to me. She gave me a look. And so that's pitch. Pitch is how high or low a sound is. Now, interestingly, pitch is it depends on, and it categorized by the frequency. It's determined. That's the word I was looking for. Determined by the frequency. The pitch is determined by the frequency. When we talked about frequency last chapter, frequency, the units for frequency are hertz, and what a frequency is how many cycles there are per unit time. So you can have a certain amount of cycles per month, per week, per day, per hour, per minute, per second. Whatever thing that you're doing, you could have however many, it's a rate, how many of those things per unit time. You know, you could have how many bike rides you take per month. If you do that out, that's a frequency. How many apples you eat per week, that's a frequency. How many naps you take per day, which nap for some of you might be a lot. That is a frequency, right? But here we're talking about the frequency of sound, and which is measured in hertz, and the frequency of sound gives us the pitch. That's what we're hearing when we hear pitch. When we hear high sounds and low sounds, we are hearing the frequency. So I discussed the muscles in your throat last time, and so what's happening is, if you remember, is they are vibrating, they are moving at different speeds. A lower frequency means, each second they're moving back and forth less times than a higher frequency, which would be more times. And that gives us the pitch. A low pitch is less movement per second. A high pitch is more movement per second. And that's what I was discussing, where naturally, generally, men have lower voices than women. What does that mean? What that means is generally the natural rhythm of our muscles in our neck for men move naturally at slower rates, where women move naturally at higher rates because they generally have higher voices. That's what is causing that to happen. We are now, that's not for everybody, and even within each gender, some guys have lower voices. I have a high voice for a guy. That means that my muscles in my neck can move different speeds. If you have a singing range, for instance, some people have a range a certain size. Some people have a larger range, a smaller range. If somebody has a larger range, that means that they can move their the muscles in their larynx at a wider variety of speeds. And you can actually train, just like you train. It's frozen. Just stay with me; it'll unfreeze. You can actually train to just like you do muscle training. You can, basketball players that can learn to jump higher because they're training the muscles in their legs. You can train to expand your range, your singing range. You can work your muscles in your throat out by doing it responsibly. You don't want to overwork them, just like you don't want to overwork any other muscle of your body when you're working out. If you're sitting there going from doing 10 reps with a 15-pound weight, and all of a sudden you try to go to 100 reps with a 50-pound weight, you're going to hurt yourself. And so you don't want to go crazy with your throat muscles, but slowly over time you can build up and you can really widen your range. I did that myself. I have a much wider range now than I did before, because your neck muscles are a muscle just like anything else that you can work out. So the pitch is given by the frequency. Now, as I also mentioned last time, there are certain frequencies that we can pick up. Anything below 20 hertz, we can't really hear naturally, but interestingly, we can sense it. 20 hertz, which is 20 frequencies per second, if you will, 20 cycles per second. We don't hear them. So if there's something vibrating at less than 20, like 17 or 18 hertz at 20, we wouldn't hear it. But interestingly, we actually feel it. So there are some times that some people feel people have described kind of a sense of I don't know how they describe it, sense of dread, and they kind of walk into a building or walk into a house and they kind of get hey man, I don't like the feeling I get in here. Now some of that might be just because you look around and you see criminals or something. Well, that might be one reason, but if you just walk into a building and all of a sudden you're like, for no apparent reason, you're like, whoa, I just feel weird. What you might be feeling is just low frequency vibrations, because it's a disconnect between your brain and your body. Your body is sensing these vibrations, and they're feeling. And if you sense the vibrations and you heard something, your brain would just go, oh, that's the reason. That's the reason why I'm feeling these vibrations. But because you're not hearing anything, there's that disconnect with your brain, and your brain is going, whoa, that's weird. And I don't know what, and so it kind of gets worried. And so we can hear things from 20 hertz all the way up to about 16,000 hertz. That's pretty high, but interestingly, the higher sounds can be heard by different other animals. For instance, you hear a dog whistle. You see somebody blow on a dog whistle and it looks like it doesn't even make a sound. Well, it is making a sound. It's just a higher frequency than we can hear, but dogs can hear it. Cats can hear it too. Cats actually have a really good sense of what really high frequencies that they can hear. Actually, I have my little kid science book with me. I happen to have it right here, and they actually have a little chart of what animals can hear what, and so I can give you an example. A human can hear somewhere between, as I said, up to about 15, 16,000, maybe even up to 20,000 hertz. A dog can hear up to 50,000 hertz. So we can hear from 20 hertz to around 20,000 hertz max. A dog can hear from 15 hertz, so slightly lower than us, all the way to 50,000 hertz, so about twice as high. Cats are around that same one. A bat can hear all the way up to 120,000 hertz. So you hear all those high frequencies, squeaks that the bat makes. You can't even hear the highest ones that they make, and they're using that for echolocation and bouncing off of things. And dolphins can go all the way up to 150,000 hertz that they can hear, and so they again use echolocation as well. The animals that use echolocation can hear really, really high sounds. Interestingly as well, as you get older, the range that you hear on your ears actually gets less and less. It's as your ears get worn out, just like anything else, and you get to be an old man and go, huh, what are you talking about? I can't hear you. But it's kind of the same thing happens to your ears. Mrs. Hanley's shaking her head now. Same thing happens to your ears in that it gets less and less. If you could hear 20,000 hertz when you were 20 years old, you might only be able to hear 15,000 hertz when you're 40, and you might only be able to hear at 12,000 hertz when you're 60 or something like that. And there's actually an interesting video on YouTube. I will post it in the assignments, and I want you to listen to the video and see what age you are when you can stop hearing the video, because it's going to start, or I should say, some of the videos are stop hearing the video, and some of the videos are start hearing it. So it's actually, I think I'll do the one where you start hearing it. So it'll start from a really, really high sound, and until 1 year old, 2 years old, 3 years old, stuff like that. And you tell me how old you were when you heard that sound. Last time I did it, I think I was like 40 or something. So you tell me how old you were. And so that was frequency, that's pitch. The other thing that we're going to talk about is loudness. Pitch corresponds to the frequency of a sound wave. Loudness corresponds to the amplitude of a sound wave. You guys remember amplitude is how far away from equilibrium that wave is. And if you think of the amplitude of an ocean wave, it's like how tall the ocean wave is, right? Now think about it. An ocean wave, the taller an ocean wave gets, the more power, the more likely it is going to be to knock you over, right? Well, the amplitude of a sound wave, the louder it is, the larger amplitude you're going to have. And the amplitude of the pressure wave is going to give you a louder sound. We have a special unit for loudness called decibels. Technically, the unit for sound, for volume, we call it volume, the unit for loudness is the bell, named after Alexander Graham Bell. However, the bell is a logarithmic scale, and so it gets 1 bell and 2 bells and 3 bells. If you don't know what a logarithmic scale is, I'm back. Good, I'm not frozen anymore. A logarithmic scale is one that is 10 times more than the other. pH scales are like this. You guys probably remember that from chemistry last year. That means if you have a 5, that's 10 times bigger than a 4. A 6 is 10 times bigger than a 5. A 7 is 10 times bigger than a 6. That's the way it is. So on the Bell scale, when you have 1, 2, 3, 4, 5, it goes up really, really fast. That's the Bell scale of sound, of loudness. So what they found was that it wasn't really useful. So instead they wanted to use tenths of bells, and instead of doing like 1.6 and a 1.7, 1.8, like that, they just decided to move the decimal over and use decibels. Just like you have like decimeters, you have decibels. And so when we have 10 decibels, or let me use a different number. When I have 15 decibels, what that is 1.5 bells. When I have 37 decibels, that's 3.7 bells, right? So it's a logarithmic scale moved over a decimal point. Okay, those are decibels. And you see on the bottom of page 406, that is the scale related to normal things. 10 decibels is barely audible. It makes it so that 0 is basically in an average human what you can't hear anymore. And there are ways that you can have negative decibels, and I'll talk about that in a second. But 10 decibels barely audible, 30 decibels like a whisper from like 3 feet away, 50 decibels again because it's a logarithmic scale. So 50 decibels, remember, would be 10 is or 20 is 10 times bigger than 10, 30 is 10 times bigger than 20. Go to 50, and it's a normal conversation. Like what I'm talking right now is probably around 50 decibels in this room. You have traffic would be like 70 decibels. An alarm clock, one of those alarm clocks would probably be around 80. You have a siren that just goes by you. Now you get to the point that it gets really loud, right? Your alarm clock might be annoying, but you don't necessarily have to block your ears. A siren going by you is like, whoa, it can freak you out and you cover your ears. That's about 100 decibels. A loud concert could be 110, 120 decibels. A jet engine, and on those things is when it's starting to be damaging to your ears, is when it's like 90, 100 decibels for a long amount of time, prolonged exposure. And the higher these decibels go, the more damage they can go to your ears. Like obviously if it's 80 decibels for a prolonged amount of time, even traffic, heavy traffic, you can lose your hearing for a long, prolonged amount of time. But once you get to like 140 decibels, which is a jet engine, even short amounts of time, you can do damage to your ears. That's why you see those guys with the sticks and stuff like that going for planes. They wear those big ear protection to protect their ears. Now, picture this. How crazy is this? You have 140 decibels. And remember, each 10, because it's a decimal, it's ones with decimal moved over, each 10 is 10 times as much. You have the biggest one that you have on there is a jet engine at 140 decibels. What you don't have on there is the space shuttle. When the space shuttle was launched, they they clocked it at 215 decibels. Picture that a rock concert is just over 100. A jet engine is 140. The space shuttle is 215. Now, if you remember, if you've ever seen the picture of the rocket going up, right, up in space, what do you see? You see obviously fire coming out of the bottom, but you see huge plumes of smoke going up, right? And everybody always assumes that's due to the fire, and some of it is. Some of it's due to the fire and the combustion of the gases, but actually a lot of that, believe it or not, is not actually due to the fire. A lot of that is due to water, which they actually spray water on the space shuttle while it's being launched. They spray water at it. Why? Because it dampens the sound. Because the sound coming off of those engines is so unbelievably powerful that it would vibrate and shake the towers and the nearby, and it would just destroy the sound. The pressure wave coming off that would just destroy the nearby buildings. So what they do is they spray it with water, and it's such a loud, powerful sound wave, a pressure wave, that it vaporizes the water, the liquid water, into a gas instantly, and that's a lot of the plumes that you see coming up. And obviously you also have the smoke from the fire. I've been speaking for 16 minutes already. I was going to talk about Doppler effect tonight, but I guess I will talk about that tomorrow, and we'll deal with Doppler effect. So your homework tonight is going to be to listen to that YouTube video and tell me, post in the comments how old, not in the comments on the YouTube video, but the assignment, how old are your ears?